Okay, welcome. So we're going to discuss in this video the connection between electron current, drift speed, and the overall electrical current, as well as define a quantity that we're going to call current density and get a bit of a sneak preview of the connection between that and Ohm's law, which we have yet to formally introduce, but turns out to be one of the more important equations within electricity and magnetism outside of Maxwell's equations themselves. So we want to draw what we've learned about electron current and connect that to electric current. We remember that electric current is the rate of change of electric charge with respect to time at a given location. And so we start off there and say that's what we have. The rate of change of charge with respect to time. Then for our charge carriers in metals and conductors, where the charge carriers are electrons, that's the number of electrons passing through that space per unit time, multiplied by the charge on an electron, or our fundamental charge, E, to give us the magnitude. So E, our fundamental charge, times the number of electrons, divided by the time it takes for that specific quantity of electrons to pass through. And again, we're dealing here, we've gone from the differentials to the deltas because we're really dealing here with averages of moles and moles, like 10 to the 20, 8 electrons and so on that are moving along here. So the averages over those large numbers are pretty much all that we need to worry about rather than specifics. So we've got that. And then we saw here our definition of electron current then was the number of electrons divided by the time it takes to move through that place. So we can put that in terms of electron current. Electrical current is fundamental charge times electron current. And then we have a relationship between that and our drift speed. So electric current in terms of drift speed goes like elementary charge times the electron density, number of electrons per unit volume, times the cross-sectional area of our wire. Recall we're looking at electrons traveling at some drift speed through a wire with a cross-sectional area of A. And so we have that. And then we want to express that in terms of the electric field, because we recall that in all of this, we have some kind of electric field going through our conductor, and the electrons themselves are bouncing around and have this net motion in the direction of the electric field. We can work with it in this way, with that substitution, And we get let's see, times E times N sub E times A, and we'll bring all that over, times E again, tau over M E. And we can simplify all this loveliness. And express it like so. Now, we're going to define a quantity here that is related to electric current, but we're going to call it the current density. And we're going to use the symbol capital J to represent it. We've used J before as our symbol for impulse, our change in momentum. However, we're not playing with momentum so much here, so we're going to go ahead and use J again. And rather than with usually when we're talking about density, we're talking about a per unit volume thing. Current density is per unit area. It's per cross-sectional area. So current divided by the cross-sectional area that current passes through is our current density. And so we do that and put our equation for current that we determined before in here, and we get that it's equal to fundamental charge squared times the electron density divided by the mass of our electrons times the time between, the average time between collisions, the mean collision time, times that cross-sectional area, and then divided by that cross-sectional area again. So they get to cancel. And we're left with this current density is all this combination of quantities which are all fundamental properties of nature, like electron charge or proton charge, what have you, or electron mass, or they're properties of the material, the number density for the electrons, the time between the drift, the mean time between collisions for those charge carriers. And when we look at this, we see that the current density is proportional to the electric field imposed across that conductor by some constant that is dependent upon material properties. And so we're going to give this constant a name. We'll define this thing. And because when this thing gets bigger, you get a bigger current density with the same electric field. It's going to get bigger the better of a conductor you've got. So we're going to call that quantity conductivity. And we're going to use the Greek letter lowercase sigma, which is this symbol here. And so for metals, conductivity is this quantity that we had in parentheses over there. And when we put that into our equation here for current density, then we get J equal to sigma E. And this is one of our big equations in electricity and magnetism. And it is a version of a relationship we're going to see later when we look at electric circuits, called Ohm's law. Named after a fellow by the name of Georg Simon Ohm. And so that's where we have it. So that'll wrap up for here, and the next time it will be on to electric current resistivity and resistance.